The second most important block or the most important module that we are going to use will be the PWM block. So this block mainly works such that it will have a reference value and it will automatically generate these two inverted PWMs for a given leg. Now we see the settings for this. We have the module number, we have different modules, it's ePWM 1, 2 and 3. So the legs that are connected are now connected for ePWM 1, 2 and 3. After that we have the timer period units, because the units cannot be set in seconds, because the system doesn't know how at which frequency it will run. So we are setting this value. This is the timer period unit, so this will be in clock cycles. In clock cycle means that it will be dependent upon the frequency of the controller. So it will work on the frequency that the controller is operating on. After that we have the timer period via. So how do you want to update the timer period? If you want a static timer period, you can set it to specify via dialog, and you can set the clock cycles here. But because we want the timer period to be calculated on the basis of a parameter, so we will use the input port option here, and we will set an initial timer period. After that we have the timer reload of timer base period registers. So it means that when the timer period will be updated, so this value is it going to update immediately after we write a new value, or it will be updated somewhere else. So in this case we have configured it to counter equals to 0. This means that after at this timer reset or timer rollover event, this timer period value will be updated always. After that we have the counting mode. So we have different modes. We have up, down and up down mode. So in up mode we will have a triangular wave. It will be like a sawtooth wave. In the down mode we have similarly a sawtooth wave in the in another direction. But in as we are using a up down mode, so this will create a center aligned PWM. Center aligned means that the each PWM will be aligned at the center of this reference triangular wave. So it will be up down. So up down, it means that the the timer will count first up and then down, then up and then down. Next we go to the ePWM A and ePWM B. So this ePWM A can be represented by channel 1 PWM. So this channel 1 PWM is ePWM A, while the channel 2 PWM is ePWM B. Now we have the configurations here. We will enable the PWM1A because we want this PWM to be outputted, so this will be enabled. So action when counter is equal to 0 and action when counter is equal to period. So this is the value then when counter is equal to 0, and this is when counter is equal to period. So out counter equal to 0, we don't have to change this PWM because it's center aligned. We don't want to change it here. And similarly at counter is equal to period, we don't want to change the state of ePWM A or channel 1 PWM. So at these points it will do nothing. After that we have clear and set. So this is up count mode. So in up count mode, what will it do when it's up counting and it crosses the reference red signal? When it crosses the reference red signal, it will be cleared. So PWM A will be cleared whenever it crosses this line. After that, in the down counting mode, so this is the down counting mode. In the down counting mode, whenever this crosses the red signal, it will change to 1. So then we set it to set. After that we go to the ePWM-B. It's the same case for ePWM-B. This is the ePWM-B. So in ePWM-B we don't do anything at 0 and at the time of period. What we do is when we in the up counting mode we will change it from 0 to 1, while in down counting This is the down counting mode, so we will change it back from 1 to 0. So this will generate a PWM. Now how do we change this value of reference? Where do we get this value? So this is the counter compare. So this compare value is the one that is the red value. So because this value is going to be calculated from this control loop and will be changed at every timer reset event. So at the timer reset event we want to change it dynamically, so we configure it to input port, so it will be changed at the input port, and we want to change it at the timer reset event. So reload from compare register. So when will it reload? It will reload at counter equal to 0. So this is the timer reset or counter equal to 0 event. So at this point this new red value will be updated here. So this red value is the compare value. So you get the compare value and you update it in each cycle. So we don't have to change anything else for this. We are only using one compare value, so we will ignore the others. After that we have the deadband unit. So in the deadband unit, this configures the dead time. So in each inverted pair, as you will be familiar with this concept, we have to have a dead time, because the switching on time of switch and switching off time of a switch is comparatively large. So there may be a time when both turn on at the same time, depending on the value or the type of the switch. So we insert dead time to compensate for this phenomenon or prevent us from the shoot through. So we will configure both PWM1A and PWM1B for the deadband. So whenever there's a in the deadband, both the channels will be 0. They will not be inverted from each other, they will both be 0. So we want the deadband to be changed from a parameter inside the model, so we configured it to input port, and we give them an initial value that it starts from. After that we have the event trigger. So in the event trigger we have the ADC start of conversion for module A. So we want to start, because as we have already discussed, that we want to start the conversion of module A from this event. So whenever there's a timer reset, so we set it to counter equal to 0. So whenever counter equals to 0, this will be the timer reset or timer rollover event. Whenever it equals to 0, the module start of the ADC will start the conversion. So this will start the ADC conversion at this instance. So at each timer reset instance, which we will trigger the ADC conversion. After that we have the trip zone unit. So um, imagine that you want to control the PWMs. You don't want to change the duty cycles, but you want to just enable and disable the inverter. So how can you easily achieve them? So for easily achieving this, we have a trip zone unit. So this will, whenever a 1 is applied to this trip zone register, it will disable the output. So we configure it to input port. We will enable it through a parameter. So whenever we want the PWMs to be enabled, we give a 0 to this input. Otherwise we will go to give it a 1. So this is a detailed preview for the PWM module.